Welcome to MEI Mechanics. We're on the topic Mechanics Basic Principles, and this is video 1.5, SUVAT equations. Now, SUVAT equations deal with any situation in which the forces acting on a particle are constant and are therefore producing a constant acceleration. And it's really important to be aware from the outset that that's the only situation in which these equations apply. If you ever meet a situation where the acceleration depends on time, so it's not constant, then you can't use the SUVAT equations. So, as a particle accelerates, acceleration means changing velocity over time. So, with that constant acceleration, its velocity will be changing at a constant rate. And because it must have velocity then, if the velocity is changing, then it will have a displacement from its initial position that will also be changing. And so we will then calculate all the changes that take place, the various variables, with the variables defined in the following way. So we use the letter S to stand for the displacement of the particle from its initial position. That means that at its initial position, when t is equal to 0, when time is 0, the displacement will be 0. And then u stands for the initial velocity, so that's the velocity at time t equals 0. And v is, well, you can either think of it as the final velocity at the end of a particular journey, or if we're thinking of this as something which is changing over time, it's the value of the velocity at time t. A is the value of the constant acceleration. Often that will be the same as the acceleration due to gravity, so 9.8 meters per second downwards, but not always. And t is the time taken for that specific journey, or the time at which the values of s and v have the values which we're assigning to them. And obviously the reason for these things being called the SUVAT equations that we'll see in a moment is because those letters spell the word SUVAT. Alright, now to help us think about these equations, where they come from, we can think about a velocity time graph for a particle which has a constant acceleration. So because the initial velocity is u, we can see there that this graph must start at u. Then the particle moves for a time t, so this is where at time t, and at that point it has velocity equal to v. Now the acceleration is the rate of change of velocity, so that will be the gradient of that line, so you can see the acceleration within this graph. And if you know much about velocity time graphs, you'll know that the displacement is equal to the area underneath the velocity time graph. So that makes sense. You can imagine if this thing wasn't accelerating at all, if it was just moving at constant velocity along this line here, so constant velocity u for time t, then distance is speed times time at constant speed, so that would be ut, and that would be the area of this rectangle. And so the same principle can be applied for the whole of this. So if I was to add this rectangle to this triangle, then that would give me the displacement that takes place as we go from time 0 to time t. So because the acceleration is the gradient of that line, we know that this change in velocity, this change in height of the graph here, will be v minus u, and that's happening over a time t. So that gives us this a equals v minus u over t. And we can rearrange that if we wish to say v equals u plus at. So the displacement is the area of this rectangle and this triangle together, which make a trapezium. And so the area of the trapezium is the average of this height and this height multiplied by this width. So it's a half of u plus v, so that's the average velocity multiplied by t. So s equals a half of u plus v times t. Or I could split that into the rectangle and the triangle and say that s equals ut plus a half of v minus u times t, because remember v minus u is that distance there. And if I remember that v itself equals u plus at, then I can replace v with u plus at, expand the bracket, simplify it, and I get s equals ut plus a half at squared. Now another way of looking at this trapezium is to think of it as being this larger rectangle with this triangle here subtracted. And of course this triangle here is the same area as this triangle here. So another way of writing the displacement is to say that it is vt, which is the larger rectangle, minus a half v minus ut, and again I can replace v minus u with at, and that gives me s equals vt minus a half at squared. So the only difference between that and the previous one is that it's a minus instead of a plus, and a v instead of a u. And we can, there's one of those that we've not mentioned yet, but this could be a challenge for yourself to try and derive this one here. But altogether this is what we have. These are the 5 Suvat equations. Now it's worth learning these actually, because they're incredibly useful and they can just be wheeled out as and when you need them. But it's also worth just having a look at the structure of them, and in particular looking at why we have 5, why we need 5, and what is it that is special about each one. And if you look carefully at this, what you realise is that each one of these Suvat equations involves exactly 4 out of the 5 variables, and obviously then therefore leaving one of the variables out. And it's there's, for each variable that we leave out, there's an equation. Okay, so those 5 variables there are the ones which are left out. So what this means is that in any situation, as long as we can identify 4 of these variables, and 3 of which we know, then I can always work out the 4th. Or another way of saying that is that if I know any 3 out of those 5, then I can work out the other 2. There'll be an equation for each of the other 2, which I can use to work those out. So let's have a look at an example. We'll see these being used now. So a particle is moving to the right, and the right is being defined as the positive direction here. So it's got an initial positive velocity. You can see there this arrow indicating the start of its motion. But it has a deceleration of 1.5 meters per second squared. In other words, it's accelerating to the left, which means that as it's moving to the right, it's slowing down. Once it's come to rest momentarily and then turned round and is now moving to the left, it's now speeding up. And we're told that the particle passes the origin with a speed of 12 meters per second. So that's what we're going to take as our initial velocity. And we're being asked to find the speed of the particle after 10 seconds. Pause. So let's start by identifying the Suvat variables, and in particular writing down any of them that we know the value of at this point. So first thing we're told, deceleration of 1.5 meters per second. So that means that our acceleration, the acceleration in the positive direction, is minus 1.5. We'll be working with units of meters and seconds throughout. The next thing we're told is that passes the origin with a speed of 12 meters per second. Now, careful, that speed is a scalar variable, but we can see it's passing the origin, it's moving to the right. So, its velocity is positive 12 meters per second at that point. Its initial velocity, which remember is u, so u is 12. and then we'd ask to find the speed of the particle after 10 seconds. So at the initial point we have t equals 0. 10 seconds later then t will be equal to 10. So that's good. As long as we've got 3 of these variables, then we can work out anything that we want to work out. The thing that we're trying to work out at this stage is what the speed is after 10 seconds. Well, we can't work out the speed directly. What we need to work out firstly is the velocity, and then we'll be able to see from that whether it's positive or negative, but we'll be able to deduce the speed from it. So it's v, which is really the thing which we are wanting to work out. So what I need to look for is a Suvat equation that involves all 4 of these variables. So let's just look back at that list, and can we find one that involves a, u, t and v? And in fact, yes, the very top one does. That v equals u plus at. So that's all that we need. So let's write that one down. V equals u plus at. Let's write that here. V equals u plus at. We know that u is 12. We know that a is minus 1.5. And we know that t is 10. Okay, so that means that v is equal to minus 3. And so the speed, because the speed's a scalar, it has to be positive. The speed is 3. And for our final answer, we should include the units. Meters per second. Alright, there's just a tidier version of the same thing there. Now there's this is a 3-part question, so part B now is going to be asking us something slightly different. It says a particle moves to the right with a deceleration of 1.5 meters per second squared. So that's the same as before, isn't it? Got the same information as before, but this time it's asking us for the time it's going to take for this particle to return to the origin. So let's think carefully then about what that means. Firstly, hopefully you're happy that we still have an acceleration of minus 1.5 meters per second squared, and we still have an initial velocity of 12 meters per second. We're asked to find the time, so we don't know what the time is, but that is involved in the question. And then it's this thing here which we need to think about carefully, the time taken to return to the origin. What does that actually mean? Well, at the origin the displacement is 0. So what it's really saying is that s is equal to 0. Now you might be thinking, well, hang on a second, that's the same as the initial displacement, so how's this going to work? Well, let's just trust the equations and see what happens. Okay, that will reveal itself. So we've got these 4 variables now. We've got a, s, u, and t. So if we just look back then at the Suvat equations, we can see that there is the second one from the bottom here, which involves those 4 variables. So we're going to use s equals ut plus half at squared. Let's write that down. So s equals ut plus half a t squared. And then let's write in the variables that we know. So that's 0 is equal to 12t plus a half a, so that will be minus 0.75, times t squared. And what we can see then is that that's a quadratic equation in t. It's a particularly nice quadratic because we don't have a constant term, so I can easily factorize that as t and then 12 minus 0.75t. So that means that either t equals 0 or 12 minus 0.75t equals 0. And if I rearrange that, I will get t is equal to 12 over 0.75, which is 16 seconds. So we've got two answers, but hopefully you can see what's happened here. We mentioned earlier this s equals 0. That's also the displacement when we're at the start. So it's no surprise that it's come out with a value, a possible value t is 0. But the one that we want is clearly this one. Yeah? To return to the origin is 16 seconds. Now on to part C then. So now we're being told, again, the same information as before in terms of the acceleration and the initial velocity, but it wants the total distance travelled in the 16 seconds. Now, we need to be careful here because we can't deal with the displacement over the whole journey because it's going that way at first and then it's coming back, and so the displacement is 0. So what we need to do in this case, if I want the total distance travelled, is I need to split this up into the part in which it's travelling to the right, and then, well, the part where it's travelling to the left, which is obviously going to be the same distance. So we need to think about what's going to happen at this special point here. This is the point that we need to focus on, where it changes direction. What's special about this point? Well, actually we've got two choices. There's two things that we can say about this point, and I think it's actually probably worth thinking about this in two different ways just to give you that option. One thing you can say about this point is that because that's where this thing changes direction, so it's slowing down, and then momentarily stopping, is we can say that at that point v is equal to 0. So I'm just thinking about the first half of this journey. If that's now my new journey is just the first half, then I can say that v is equal to 0. I know that a is minus 1.5. I know that u is 12, and what I want to know is s. So that's one option, one way of starting it off. Another way we could set this up is to say, right, what else is special about that point? Well, it's halfway through the journey. You need to it's a bit of a leap of faith here if you're not familiar with these problems, but what is going to happen is this section of the journey and this section of the journey are really almost like reflections of each other. They're over the same distance, you've got the same size of acceleration taking place, and you've got a point of 0 speed at one end. And what that means is that the time for both those sections of the journey is going to be the same. So if we apply the idea that the time is going to be half of the time for that whole journey, we know that the time for the whole journey is 16, so if I say that t is therefore now equal to 8, again I've got the same acceleration as before, I've got the same initial velocity as before, and I need to know the displacement. So I've got two options. So it'd be nice to look at both of these. You can decide which one you prefer, and just check that they both give us the same answer. So let's look back at the Suvat equations and decide which Suvat equation we're going to need. Firstly, for this situation where we've got V, A, U, and S. So it'll be this one. That's actually what you can write here. Or if we're looking at if we're doing it this way, where we've got T, A, U, and S, then it's this equation here which is going to be the one to use. So that involves those four variables there. So let's write that in there. So equals ut plus half at squared. Alright, so let's turn attention to this one firstly, see what happens here. So v squared, well that's nice because I know that that's 0, so 0 squared is 0 as well. U squared, so that's 144 plus 2 times minus 1.5 times this s that we're trying to find. So, well, 2 times minus 1.5 is 3, so that's 144 minus 3s. So that means that s is going to be 144 over 3, which is 48 meters. But bear in mind, that's just for the first half of the journey. It then travels 48 meters again in the other direction. So the total distance travelled is double that, which is 96 meters. Alright, what if we did it this way? So this was relying on the idea that this will be halfway through in terms of the time, and we've got this. So s, that's the unknown, is ut, so that's 12 times 8, half times minus 1.5 times 64, because t is 8, so t squared 64. And if I work that out, that thankfully comes out as 48 again. Okay, so of course again the total is 96 meters. So I think it's nice to see that often there are two different approaches to the same problem. Certainly when you're practicing this at home, it's worth trying both those. Check you get the same. See if you can see why they both work. And obviously, if you ever found that they weren't the same, then that would be a good way of realizing that something's gone wrong. You can go and look into it and see if you've got a misconception or if you made an error somewhere. Now, it may have occurred to you, I'm not going to go through this in detail, it may have occurred to you that there was possibly an even quicker option here, which is if we use both of those things, so both the fact that v equals 0 and the fact that t equals 8, then there's another Suvat equation we can use that involves both of those as well as u and s, and that's arguably easier again. But all three of those approaches work. They all give you the same result in the end, so it's reassuring to see that. So that concludes video 1.5 using the Suvat equations. The next video will be video 1.6, resolving forces.